Saturn looks like the most stable picture in the solar system. A calm golden world, perfectly framed by rings. But Cassini taught us something unsettling. Saturn is not a timeless icon. It's a system caught mid-change. The planet is leaking clues through its storms, its magnetic field, and even through the ring particles that are quietly falling into its atmosphere. And the rings, the very thing that defines Saturn, might be far younger than we ever imagined, or far older than we can comfortably explain. Two ideas can both fit part of the data, and neither fits everything. Then there are the moons. Some look like quiet ice, but inside they carry signatures of hidden oceans, violent cracks, methane weather, and geysers that spray water into space. So tonight, we're not just visiting Saturn. We're stepping into a mystery. What Saturn really is, and what it's slowly becoming. And if Cassini was right, we may be living at the exact moment this story is still visible. For most of human history, Saturn was not a world. It was simply a light. To ancient sky watchers in Babylon and Greece, Saturn appeared as a bright, yellowish point that moved slowly across the stars. In 1610, Galileo Galilei pointed his early telescope toward Saturn, expecting something familiar, a simple disk, like the moon or Jupiter. What he saw didn't fit that picture at all. Saturn appeared stretched, almost as if it had two small shapes attached to its sides. Galileo described them as ears, giving the planet a strange, three-part form. He assumed they might be moons, but they didn't behave like moons. They didn't move. They didn't circle Saturn. They stayed fixed in place. Galileo carefully recorded what he saw, even though it made little sense. His telescope was crude and blurry by modern standards, but the image itself was real. Saturn truly looked that way from Earth at the time. Then, a few years later, something even stranger happened. When Galileo looked again, the ears were gone. Saturn appeared smooth and round, as if nothing had ever been there. Galileo wrote that the planet had swallowed its children. He had no way to explain why Saturn seemed to change its shape. But Saturn wasn't changing. Our view was. The confusion Galileo left behind did not last forever. In the middle of the 17th century, a new generation of astronomers began to look at Saturn with better instruments, and with a fresh willingness to question what they thought they were seeing. One of them was Christian Huygens. In 1655, Huygens proposed a simple but powerful idea. Saturn was surrounded by a thin, flat ring, detached from the planet itself. It was not two companions. It was not a distorted shape. It was a structure, wide, circular, and tilted relative to Earth. That single insight resolved decades of confusion. The ears Galileo had seen were not moons at all. They were the bright edges of a ring, viewed at an angle his telescope could not separate. When the ring tilted edge on, it disappeared. When it opened again, it returned. For the first time, Saturn made sense. In the same year, Huygens also discovered Titan, Saturn's largest moon, a world so distant and slow-moving that it had remained invisible to earlier observers. With Titan, Saturn was no longer just a planet with a ring. It was a system. A few years later, another name entered the story. Giovanni Domenico Cassini turned his attention to Saturn and noticed something Huygens had not described. The ring was not uniform. It was split by a dark gap, a vast division separating one ring from another. Today we call it the Cassini division. Cassini went on to discover several more moons, each moving in slow, deliberate paths around the planet. Saturn's family was growing, and its complexity was becoming harder to ignore. By the end of the 17th century, Saturn was no longer a simple light in the sky. It was recognized as a structured system, rings, gaps, and orbiting worlds, all bound together by gravity. And yet, even with these breakthroughs, something remained out of reach. Everything Huygens and Cassini learned came from a great distance. Through lenses, through faint light, through patient observation, but never direct contact. Saturn was clearer than before, but it was still far away. The name Cassini would return centuries later, not just to observe Saturn, but to finally stay with it. By the late 20th century, Saturn was no longer just something we observed from afar. For the first time, humanity sent machines to cross its path. The first was Pioneer 11. In 1979, Pioneer 11 became the first spacecraft to fly past Saturn. It did not carry sophisticated cameras by today's standards, but it did something far more important. It proved that a close encounter was possible. Pioneer 11 skimmed past the planet and its rings, measuring Saturn's magnetic field, sampling charged particles, and sending back the first direct data from the Saturnian environment. And then, Pioneer 11 was gone. A year later, Saturn was visited again, this time by Voyager 1. In 1980, Voyager 1 swept past Saturn with far better instruments and cameras. What it revealed changed Saturn overnight. The rings were not smooth or simple. They were layered, divided, and filled with fine structure. Countless narrow bands, gaps, and subtle patterns that no telescope on Earth could resolve. Voyager 1 also discovered new moons and captured close-up views of familiar ones, revealing surfaces shaped by impacts, fractures, and gravity. Then, in 1981, Voyager 2 followed. Voyager 2 refined what Voyager 1 had begun. It added detail to the ring system, discovered additional moons, and confirmed that Saturn's environment was dynamic rather than static. The data hinted at interactions between rings and moons, gravitational relationships that sculpted gaps and waves in the rings themselves. Together, the Voyager flybys transformed Saturn from a distant curiosity into one of the most intricate systems in the solar system. But they could not see change. They passed through Saturn. They did not stay long enough to watch it evolve. And that left a lingering question. If Saturn's rings, moons, and magnetic field were this complex during a brief flyby, what would they look like if we stayed? That question would define the next chapter of Saturn exploration, and it would require a very different kind of mission. Everything changed in 2004. That was the year Cassini reached Saturn, not for a quick pass, but to stay. After a long journey through the solar system, the spacecraft fired its engines and slipped into orbit around the planet. For the first time in history, Saturn was no longer something we visited briefly. It became a place we lived with. In 2005, Cassini did something no mission to Saturn had ever done. It released a small probe named Huygens and sent it toward Titan, a moon hidden beneath a thick orange haze. As Huygens separated, the probe drifted slowly downward, carried by parachutes through Titan's dense atmosphere. For more than 2 hours, it descended through layers of cold air and cloud, recording pressure, motion, and light as it fell. Below, the surface remained invisible. And then, Huygens touched down. There was no crash, no splash. The surface gave way slightly, firm, but not hard. For a short while, Huygens kept listening. It recorded actual sounds from another world, the faint movement of wind across Titan's surface. A real sound, captured nearly 1 billion miles from Earth. Saturn is made almost entirely of hydrogen and helium. By volume, about 96% is hydrogen, and roughly 3% is helium. The remaining fraction is made up of trace gases, methane, ammonia, and small amounts of water vapor. Just enough to shape clouds and color, but not enough to form anything solid. At the top of the clouds, temperatures are already extreme. Around -170 degrees Celsius, cold enough that water behaves like stone. As you descend, the temperature rises steadily, not in steps, but in a smooth gradient. Hundreds of degrees, then thousands. Pressure builds the same way. Gas thickens into fluid. Fluid becomes dense. And far below, where pressure reaches millions of times that of Earth's atmosphere, hydrogen changes its nature entirely. It is squeezed so tightly that electrons move freely through it. Hydrogen becomes metallic. This layer does not sit still. It flows, circulates, and carries electric currents strong enough to generate Saturn's magnetic field. A field born not from a solid core, but from motion inside a planet that never truly stops shifting. Heat is just as important. Despite being so far from the Sun, Saturn radiates more energy than it receives. That extra warmth comes from within, released slowly as the planet continues to contract under its own gravity. A quiet process, a deep one, and one that has been unfolding for billions of years. There is no sharp boundary between layers, no sudden surface, no place where atmosphere simply ends. Only a gradual descent from gas to fluid to something stranger. And all of this exists at a distance that is hard to picture. On average, Saturn orbits nearly 1.4 billion kilometers from Earth, sometimes closer, sometimes farther. Even at its nearest, light takes more than an hour to travel between our world and Saturn's clouds. From that distance, Saturn looks calm, smooth, almost motionless. But inside, hydrogen flows like metal, heat rises without sunlight, and pressure reshapes matter into forms we never see on Earth. Saturn is not built like a world with a floor and a ceiling. It is a continuous body, shaped by pressure, by motion, and by time. Saturn's atmosphere looks gentle from far away, but it is constantly in motion. Powerful winds race around the planet, flowing in wide bands that circle the globe. Some move at incredible speeds, driven by heat rising from deep inside the planet. Near the North Pole, Cassini revealed one of Saturn's most unusual features: a vast six-sided jet stream. The hexagon holds its shape year after year, rotating with the planet instead of drifting apart. Nothing else like it exists in the solar system. Storms also erupt within Saturn's clouds. Lightning flashes through the atmosphere, strong enough to be detected as bursts of radio energy. When those signals are converted into sound, they reveal sharp crackles. Saturn's storms made audible. Some storms grow large enough to wrap around the planet before slowly fading, leaving subtle changes behind. Saturn's atmosphere is not chaotic. It is structured, persistent, and powered from below. Even a planet made mostly of gas can host patterns that endure. On Earth, a day is easy to measure. The planet turns. Landmarks move. The magnetic field tilts, creating a clear signal of rotation. Saturn offers none of these conveniences. There is no surface to track. And unlike most planets, Saturn's magnetic field is almost perfectly aligned with its axis of rotation. That alignment removes one of the main tools scientists normally use to measure a planet's day. For years, researchers relied on radio signals linked to Saturn's magnetic field. These signals repeat with a rhythm that seems tied to rotation. But Cassini revealed something unexpected. The signals drifted. Over time, the length of a Saturn day, measured this way, slowly changed. even though the planet itself could not be speeding up or slowing down so dramatically. The radio clock was influenced by Saturn's atmosphere and magnetosphere, not locked to its deep interior. Cassini approached the problem differently. By tracking tiny changes in the spacecraft's orbit, scientists measured subtle variations in Saturn's gravity field. Those variations carried information about how mass moves inside the planet and how fast its deeper layers rotate. The result was not a single number. Saturn does not rotate as one rigid body. Its deep interior, its atmosphere, and its magnetic environment all move at slightly different speeds. A day on Saturn depends on which layer you choose to follow. This isn't confusion. It's a reminder of what Saturn truly is. Not a solid world turning cleanly through space, but a vast, flowing system. Hydrogen, helium, heat, and motion, all sliding past one another over time. On Saturn, time isn't marked by sunrise or sunset. It's marked by movement. From a distance, the rings of Saturn look smooth and elegant. Thin bands of light wrapped neatly around the planet. Up close, they are anything but simple. Cassini revealed that Saturn's rings are built from countless pieces of ice and rock, ranging from dust-sized grains to chunks as large as houses. Each one follows its own orbit, moving at slightly different speeds depending on its distance from the planet. This constant motion creates structure. One of the most visible features is the Cassini division, a wide, dark gap separating Saturn's two brightest rings. From Earth, it looks like an empty space. In reality, it is a region where gravity has cleared and reshaped material over time, influenced by the pull of nearby moons. The Cassini division is not a crack. It is a boundary shaped by motion. Closer in, Cassini found smaller gaps, narrow, precise openings cut into the rings. One of these is the Encke gap, a thin lane that runs through the outer rings like a groove. Inside that gap moves a tiny moon named Pan. Pan does not sit quietly. As it orbits, its gravity pulls ring particles toward it, carving and maintaining the gap. The result is a wake pattern, waves of material rising and falling around the moon's path, frozen into the ring like ripples in sand. Another small moon, Daphnis, performs a similar role within a different gap. As Daphnis moves slightly above and below the ring plane, it tugs on nearby particles, lifting edges and creating vertical waves, structures that rise kilometers high, briefly catching sunlight as the rings tilt. These moons are often called shepherd moons. They don't fence the rings into place. They guide them. Their gravity sculpts edges, sharpens boundaries, and keeps certain regions from spreading apart. Without these small moons, Saturn's rings would look far less defined. But the rings are not static, even where moons are absent. Throughout the ring system, Cassini detected density waves, spiral patterns formed by gravitational interactions with moons farther away. Each wave begins at a specific location, where a moon's orbital rhythm resonates with the motion of ring particles. At those resonant points, particles bunch together, then spread apart, creating alternating regions of higher and lower density. The result is a pattern that slowly winds through the rings, carrying information about the mass and motion of the system. In this way, the rings behave less like a solid object and more like a fluid. They respond to forces. They transmit disturbances. They remember interactions long after they occur. Every gap, every ripple, every sharp edge is a record of gravity at work, written not in stone, but in ice. Cassini showed that Saturn's rings are not decorative features. They are active structures. They evolve. They interact with moons. They change shape over time. What looks like stillness from afar is up close, a delicate balance of motion. Countless particles responding to gravity, second by second, orbit by orbit. Saturn's rings are not frozen in place. They are constantly being shaped. And that quiet shaping sets the stage for the next question. Not how the rings are structured, but how long they can last. On September 15, 2017, during its 293rd orbit, the mission came to an end. Not with silence, not with distance, but with intention. After 13 years circling Saturn, Cassini was guided onto a final, irreversible path, straight into the planet's atmosphere. The spacecraft had fuel for only a short time longer, and mission planners faced a choice. They chose to protect what mattered most. Cassini's final months were unlike anything that came before. Instead of looping safely around the planet, the spacecraft began a daring series of passes, diving through the narrow gap between Saturn and its rings, a region no spacecraft had ever entered. With each plunge, Cassini skimmed closer to Saturn than ever before. Flying between the rings and the planet allowed scientists to measure gravity with extreme precision. Tiny changes in the spacecraft's speed revealed the mass of the rings, not just their brightness, but how much material they truly contained. For the first time, researchers could estimate whether the rings were ancient survivors from the birth of the solar system, or relatively young structures shaped and reshaped over time. Cassini also sampled Saturn's upper atmosphere directly. As it plunged through tenuous layers of gas, its instruments tasted particles and fields that had never been measured up close. Every second mattered. Every bit of data was sent back immediately. There would be no second chance. The decision to end the mission this way was not dramatic for drama's sake. It was careful, responsible. Cassini was carrying Earth-made microbes. Even after years in deep space, those organisms could still pose a risk. And Saturn's system includes worlds that may host environments suitable for life, especially Titan, with its complex chemistry, and Enceladus, with its hidden ocean beneath ice. Letting Cassini drift uncontrolled was not an option. By directing the spacecraft into Saturn, scientists ensured that it would never contaminate those moons. The planet itself would act as a final shield, absorbing the spacecraft completely. As Cassini descended, Saturn's atmosphere thickened. Drag increased. The spacecraft struggled to maintain orientation. Its thrusters fired automatically, fighting to keep the antenna pointed toward Earth. For about 45 seconds, Cassini continued transmitting. Then the signal stopped. The spacecraft broke apart under heat and pressure, becoming part of the planet it had spent more than a decade studying. Cassini did not crash. It dissolved. And in doing so, it completed its mission. Because Cassini was never meant to last forever. It was meant to watch Saturn long enough to notice change, to see seasons shift, storms rise and fade, rings sculpted by gravity, and moons revealing hidden activity. It showed us that Saturn is not a static picture, but a system in motion. The rings are shaped, disturbed, and slowly altered. The atmosphere is driven from below by internal heat. The moons are not frozen relics, but evolving worlds. Cassini's final act reflected everything it had taught us. That exploration is not just about going farther. It is about staying long enough to understand what is already there. When Cassini was gone, Saturn remained, quiet, distant, still changing. And for the first time, we knew how to watch it. Not every moon around Saturn announces itself with geysers or thick atmospheres. Some tell their stories quietly, through fractured ice and surfaces shaped by time. Two of those quieter worlds are Dione and Rhea. They don't erupt, they don't glow, but they remember. Dione, a moon shaped by slow internal stress, Dione appears bright and smooth from a distance, covered in reflective ice. But when Cassini looked closer, that calm surface began to break apart. Long fractures stretch across Dione's terrain, some running hundreds of kilometers. These cracks are not random. They follow patterns that point to stress from within, caused by Saturn's gravity gently flexing the moon as it moves along its orbit. That repeated flexing does not tear Dione apart. It works slowly. Over time, the ice shell fractures, exposing fresher material beneath. On Dione's trailing side, Cassini observed bright cliffs and linear scarps, places where the crust has shifted and broken, revealing a younger surface below older, cratered ground. The contrast is subtle, but meaningful. Dione is not a moon frozen entirely in the past. Its surface suggests motion beneath the ice, quiet, stable, and long-lived. Some evidence even points to a deep layer that may be warmer or partially softened, though not active enough to erupt. Dione's story is one of endurance, a world reshaped not by violence, but by repeated gentle stress over immense spans of time. Rhea, a moon shaped by impact and age, Rhea tells a different story. It is Saturn's second largest moon, and its surface is heavily scarred. Craters overlap craters, forming a dense record of impacts stretching back billions of years. At first glance, Rhea looks like a relic, unchanged, inert, and ancient. Cassini complicated that view. High-resolution images revealed linear fractures cutting across cratered terrain. These features are older than Dione's cracks, but they suggest that Rhea was not always as cold and rigid as it is today. Some of Rhea's craters appear softened and relaxed, as if the ice beneath them slowly flowed long ago. That kind of deformation requires warmth, at least for a time, allowing ice to behave more like a very slow-moving fluid. Rhea cooled as it aged. What remains today is a surface dominated by impacts, but not untouched by internal change. Its density points to a mixture of ice and rock, layered rather than uniform, shaped by both formation and gradual evolution. Cassini also searched for rings around Rhea, an idea raised by earlier observations. That hypothesis did not hold up. What Cassini found instead was subtler, interactions between Rhea and Saturn's magnetic environment, shaping a faint, invisible region around the moon. Not rings, but influence. Quiet worlds, essential context. Dione and Rhea occupy a middle ground in Saturn's system. They are not as dramatic as Enceladus, not as complex as Titan, but they matter. Together, they show that Saturn's moons exist along a spectrum. Some remain active, some have settled into quiet. Others preserve a long memory of change, written into ice, fractures, and softened craters. These moons don't demand attention, they reward patience. And they remind us that in Saturn's system, even silence can carry a history. Some of Saturn's moons surprise us with activity. Others surprise us with contrast. Two of the most unusual are Iapetus and Tethys, worlds that look simple at first glance, then reveal features so extreme they challenge easy explanations. Iapetus, a moon split in two. Iapetus is famous for one thing above all else. It has two radically different faces. One hemisphere is dark, absorbing sunlight and appearing almost black. The other is bright, reflective, and icy. The boundary between them is sharp and unmistakable, as if the moon were painted in halves. This contrast puzzled astronomers for centuries. Cassini helped clarify what was happening. The dark material is not a surface coating that spread evenly. Instead, it likely arrived from outside. Dust from distant moons or debris falling onto Iapetus's leading side as it moves through space. Once the dark layer settled, sunlight did the rest. The darker surface warmed more than the bright ice. That extra heat caused ice to slowly sublimate, turning directly from solid to vapor. The vapor then migrated and refroze on the colder, brighter regions. Over time, a feedback loop formed. Dark areas grew darker, bright areas grew brighter. Iapetus didn't become two-faced overnight. It slowly separated itself, guided by temperature and motion. Then, there is the ridge. Running along much of Iapetus's equator is a massive chain of mountains, towering kilometers above the surrounding terrain. No other moon has anything like it. The ridge looks artificial at first glance, but its origin is likely ancient. One leading idea suggests that Iapetus once spun faster, allowing material to accumulate along its equator. As the moon slowed and cooled, that material remained, frozen in place, a geological memory of an earlier era. Iapetus is a moon shaped by extremes, not violent activity but imbalance. Between light and dark, fast and slow, past and present. Tethys, a world scarred by stress, Tethys tells its story differently. This bright, icy moon is dominated by one of the largest impact craters in the Saturn system. The crater spans a significant fraction of Tethys's diameter, a reminder of how violent the early solar system once was. But the crater is not Tethys's most striking feature. Stretching across much of the moon is a vast fracture, a canyon-like trough that runs for thousands of kilometers. It cuts across the surface like a seam, too large to ignore. This structure is likely the result of internal stress. As Tethys cooled long ago, its interior contracted. That contraction placed tension on the ice shell, eventually causing it to crack. The result is a global-scale fracture, one of the largest known in the solar system. Unlike Enceladus, Tethys shows no signs of current activity. The fracture is ancient, a remnant of a time when the moon was warmer and more flexible. What remains today is a frozen record. Two moons. Two lessons Iapetus and Tethys remind us that change does not always mean motion we can see. Some moons evolve through temperature differences and slow feedback. Others preserve the scars of cooling and impact. Neither is active today. Both are shaped by history. In Saturn's system, not every world is alive in the same way. Some change quickly, some change slowly, and some carry the marks of transformation long after the forces that shaped them have faded. These moons don't move much anymore, but they still have stories to tell, written into contrast, fracture, and frozen terrain. If any moon around Saturn feels like a world in its own right, it is Titan. From a distance, Titan appears calm, wrapped in a thick orange haze that hides its surface completely. For a long time, that haze kept Titan mysterious. Telescopes could not see through it. Even Cassini's cameras struggled at first. But Titan is not quiet. It has weather, it has seasons, and it has liquids moving across its surface. Titan's atmosphere is thick, denser than Earth's, and made mostly of nitrogen, with smaller amounts of methane and other organic molecules. At Titan's extreme cold, methane plays a role similar to water on Earth. It evaporates, it forms clouds, it rains. Cassini watched methane clouds gather in Titan's skies, especially near the poles. These clouds changed with the seasons, growing and fading as sunlight shifted during Saturn's long year. When conditions were right, methane rain fell, not gently, but in sudden downpours capable of reshaping the surface below. Over time, those rains carved channels and valleys into the ice. Cassini's radar pierced the haze and revealed branching river networks etched across Titan's landscape. They looked familiar, like river systems on Earth. But their chemistry was entirely different. Here, water is rock. Methane is the fluid. That difference changes everything. At Titan's surface temperatures, water ice is as hard as stone. It forms mountains, plains, and cliffs. Methane and ethane, hydrocarbon liquids, flow across that frozen ground, collecting in low areas. Near Titan's poles, Cassini discovered vast, dark regions that absorbed radar signals instead of reflecting them. These were not shadows. They were seas. Titan hosts stable lakes and seas filled with liquid methane and ethane, some stretching hundreds of kilometers across. Their shorelines rise and fall over time, responding to rainfall and evaporation, just as coastlines do on Earth. These seas are not shallow puddles. Radar measurements suggest depths of tens to hundreds of meters in some regions. They are persistent features tied to Titan's climate rather than short-lived events. Titan's weather operates on long timescale. A single Titan season lasts more than 7 Earth years. Storms are rare but powerful. Rain may fall only occasionally, but when it does, it leaves lasting marks. Channels deepen, surfaces darken, liquids migrate slowly toward the poles. Cassini also detected waves on Titan's seas. Small ripples caused by wind moving across liquid methane. It was the first time waves were observed on the surface of another world. That moment mattered. It confirmed that Titan's liquids are not frozen or trapped underground. They are active, responding to atmosphere and wind in real time. But Titan's chemistry goes even deeper. High in the atmosphere, sunlight breaks apart methane molecules, allowing carbon-rich compounds to form. These molecules collide and grow, eventually clumping into complex organic particles that drift downward like smog. Over time, they settle onto the surface, coating the ice with a dark layer rich in organic material. This constant rain of chemistry links sky and ground. Titan is not just a moon with weather. It is a chemical factory. Some of these organic compounds resemble the building blocks of life, not life itself, but ingredients that, under different conditions, could lead toward complexity. On Titan, those conditions are far too cold for liquid water biology as we know it. But the processes are real. They show that chemistry does not need Earth-like warmth to become intricate. It only needs time, energy, and motion. Cassini returned to Titan again and again, watching the moon change with the seasons. It tracked cloud movements, monitored shoreline shifts, and the slow reshaping of the surface. Each pass added context, turning isolated discoveries into a coherent climate system. And Titan remains active. Its atmosphere is constantly replenished, its lakes persist, its chemistry evolves. While other moons preserve ancient scars, Titan continues to rewrite its surface, slowly, patiently, and predictably. In Saturn's system, Titan stands apart. It is not defined by fractures or geysers. It is defined by cycles, evaporation and rain, clouds and clearing skies, seas that grow and shrink with time. Titan does not resemble Earth because it shares our conditions. It resembles Earth because it shares something more fundamental: process. It reminds us that worlds do not need to be warm to be dynamic. They only need the right balance of energy and materials. Beneath Titan's haze lies a moon shaped by weather, real weather, playing out in a chemistry unlike anything on Earth. And as Cassini showed us, Titan is not a frozen relic. It is a living climate system, quietly at work on the edge of the solar system. At first glance, Enceladus looks small and quiet, an icy moon barely 500 kilometers across, orbiting far from the warmth of the sun. Nothing about its size suggests what lies beneath. Cassini changed that. As the spacecraft passed close to Enceladus, its instruments detected something unexpected near the moon's south pole. The region was warmer than it should have been. Not by much, but enough to stand out against the surrounding cold. Then came the plumes. Jets of water vapor and ice particles were spraying into space, erupting from long fractures in the ice known as tiger stripes. These were not faint wisps. They were powerful geysers, reaching hundreds of kilometers above the surface. Enceladus was venting material into space. Cassini flew directly through those plumes. Instead of crashing into ice, the spacecraft passed through a cloud of water vapor, salts, and organic molecules, material that had come from below the surface and was now exposed to space. This was the moment everything changed, because geysers require a source. They need pressure, they need heat, and they need liquid. All signs pointed to a global ocean hidden beneath Enceladus's ice shell. Gravity measurements confirmed it. Subtle wobbles in the moon's motion revealed a layer of liquid water beneath the crust, extending across much of the moon. This ocean is kept warm not by sunlight, but by tidal forces. Enceladus flexing slightly as it moves along its orbit around Saturn. That repeated flexing generates heat, preventing the ocean from freezing solid. But heat alone wasn't the most surprising discovery. Cassini's mass spectrometer detected salts in the plume material, evidence that the water had been in contact with rock. This suggested hydrothermal activity on the ocean floor, where warm water interacts with a rocky core. Even more remarkable, Cassini detected molecular hydrogen in the plumes. On Earth, hydrogen like this is often produced by chemical reactions between water and rock at hydrothermal vents. Those reactions can provide energy that microbes use to survive in complete darkness. No life was detected at Enceladus, but the conditions were unmistakable. Liquid water, chemical energy, and organic molecules. The three ingredients life as we know it requires. Enceladus is not just geologically active, it is chemically alive. The geysers themselves act like a breathing system. As Enceladus orbits Saturn, tidal stresses open and close the fractures at the South Pole. When the cracks widen, water escapes. When they narrow, the flow decreases. The ocean responds rhythmically, pulsing with the moon's motion. It is not chaotic. It is regulated. Each eruption feeds Saturn's E-ring, replenishing it with fresh ice particles. In this way, Enceladus shapes its environment far beyond its own surface, affecting the ring system itself. Cassini returned to Enceladus again and again. It measured plume composition, it mapped heat flow, it tracked changes over time. What emerged was not a single dramatic event, but a stable process. An ocean that has likely existed for millions, perhaps billions of years. And that longevity matters. Short-lived water is common in the solar system. Long-lived oceans are not. Enceladus maintains its ocean through a delicate balance of gravity and motion. Too little tidal heating, and the water would freeze. Too much, and the system would destabilize. Instead, Enceladus sits in a narrow zone where liquid water can persist. Small moon. Big consequence. Unlike Titan, Enceladus does not have weather or lakes on its surface. Its activity is hidden, revealed only through fractures and vapor. But in some ways, that makes it more accessible. We don't need to drill through kilometers of ice to sample the ocean. The ocean comes to us. Cassini proved that by flying through the plumes, collecting fresh material ejected directly from below. No other ocean world offers such a direct connection between interior and space. This is why Enceladus is often described as one of the most promising places to search for life beyond Earth. Not because life has been found, but because the environment is ready. Everything essential is present, everything is active, and everything is happening now. Enceladus forces us to rethink what makes a world habitable. It does not need size. It does not need sunlight. It does not need an atmosphere. It needs motion. Gravity flexing ice. Water circulating through rock. Chemistry unfolding in darkness. In Saturn's system, Enceladus stands out not as the largest or the brightest, but as the most quietly profound. A moon where an ocean breathes beneath ice, exhaling water, energy, and possibility into space. And thanks to Cassini, we were close enough to notice. For centuries, Saturn's rings were treated as something permanent, an ornament that had always been there and always would be. Cassini changed that assumption. When scientists finally measured the mass of the rings directly, the numbers told a quieter, more unsettling story. The rings were bright, yes, but surprisingly light. Not massive enough to survive untouched since the birth of the solar system. Which raised a difficult question. If the rings are not ancient, where did they come from? One answer points to gravity, and a boundary called the Roche limit. The Roche limit marks a distance from a planet where tidal forces become overwhelming. Inside this region, a moon held together only by its own gravity cannot survive. The planet's pull stretches it, deforms it, and eventually tears it apart. Saturn's rings sit almost entirely inside this boundary. That placement matters. It means the rings are not just floating debris. They occupy a region where moons struggle to exist at all. Anything that crosses too close is pulled, stressed, and, given enough time, broken down. One leading idea suggests that Saturn's rings were born from a moon that ventured too near. Not recently in human terms, but long after Saturn itself formed. As the moon crossed the Roche limit, tidal forces overcame its internal strength. Fractures spread, ice broke free. Rock and debris followed. Over time, the remains were stretched into countless individual orbits, flattened into a thin disk circling the planet. A moon became a ring. This was not an explosion. It was a slow disassembly. Gravity did the work quietly, piece by piece. The composition of the rings supports this idea. They are made mostly of water ice, with relatively little rock. Exactly what you would expect if an icy moon were stripped apart, leaving denser material to sink inward or be lost. But there is a complication. If a moon was destroyed, when did it happen? Cassini's measurements suggest the rings may be much younger than Saturn itself, perhaps only a few 100 million years old. In cosmic terms, that is recent. That timing feels uncomfortable. Why would a moon survive for billions of years, only to be destroyed relatively late? One possibility is orbital change. Moons do not always stay where they are born. Over long periods, gravitational interactions can shift orbits inward or outward. A moon that was once safe could slowly drift closer to Saturn, eventually crossing the Roche limit. Another possibility involves collisions. A large impact could weaken a moon's structure, making it more vulnerable to tidal forces. Once fractured, the process would accelerate, ending in complete disruption. In both cases, the result is the same. A moon loses its integrity, its fragments spread, and a ring system forms. But rings do not remain pristine. Over time, micrometeoroids rain down, darkening the ice. Collisions cause particles to clump or disperse. Material slowly spirals inward, pulled by gravity and magnetic interactions. The rings we see today are not static remnants. They are evolving. This creates a paradox. The rings look young and bright, suggesting a recent origin. But the processes that form them are slow, suggesting patience rather than violence. Cassini did not resolve that paradox completely. What it did show is that Saturn's rings are not guaranteed to last. They are shaped by the same forces that created them, and those forces continue to act. The Roche limit does not just explain where the rings are. It explains why they exist at all, and why they may one day fade. If Saturn's rings were born from a moon, then they are not decorations. They are remains, a record of loss, a record of gravity at work. And like all records written in motion, they are temporary, which leads to a deeper realization. Saturn is not a planet with rings. It is a planet still responding to its own gravity, reshaping moons, redistributing material, and quietly rewriting its appearance over time. The rings are not outside Saturn's story. They are part of it. And understanding where they came from is only half the question. The other half is how long they can survive. That question is still unfolding. Saturn's rings are striking. But there is another mystery that has puzzled scientists for decades, one that cannot be explained by rings alone. Saturn is tilted. Its axis leans by about 26.7 degrees, almost as much as Earth's. That tilt gives Saturn seasons, shifting sunlight across its clouds and rings over a long year. For rocky planets, such tilts are often explained by ancient collisions. But Saturn is not rocky, and no clear impact could account for its angle. For a long time, the tilt remained an open problem. Then a quieter idea emerged, one that did not rely on a single violent event, but on slow motion, resonance, and loss. It is known as the Chrysalis hypothesis. The hypothesis begins with a simple observation. Saturn's tilt appears to be linked to the motion of another giant planet, Neptune. Over long periods, Neptune's orbit slowly shifts, causing a gentle gravitational rhythm that can influence Saturn's rotation. For that rhythm to tilt Saturn, something had to help lock the motion in place. That something, scientists propose, was a moon, a large one. This hypothetical moon, named Chrysalis, would have orbited Saturn for billions of years. Not small like Enceladus, not distant like Iapetus, but massive enough to affect Saturn's internal dynamics. As long as Chrysalis existed, it acted like a stabilizer. It helped Saturn's spin axis stay aligned in a way that matched Neptune's slow orbital changes. The system was balanced, but balance in the solar system is rarely permanent. Over time, gravitational interactions among Saturn's moons caused subtle shifts in their orbits. One by one, small changes accumulated. Chrysalis slowly drifted outward, approaching a dangerous region of space, the Roche limit. Crossing that boundary would be fatal. When Chrysalis finally moved too close, Saturn's tidal forces overwhelmed the moon's structure. The moon did not explode. It stretched, fractured, and came apart, much like the scenario proposed for the origin of the rings. A moon was lost. Its destruction had consequences. Without Chrysalis, Saturn's spin was no longer stabilized in the same way. The gravitational connection with Neptune continued. But now Saturn's axis was free to respond. Slowly, over millions of years, Saturn's tilt increased. Not suddenly, not violently, but steadily, until it reached the angle we see today. This single idea helps connect several puzzles at once. First, It explains Saturn's axial tilt without requiring an ancient collision. Second, it offers a natural source for fresh icy material. If Chrysalis was rich in ice, its breakup could have contributed debris that became part of Saturn's ring system, or replenished it. Third, it fits with what Cassini measured about the ring's mass and apparent youth. If a moon was destroyed relatively recently in cosmic terms, the brightness and composition of the rings make more sense. And finally, it explains why Saturn's moons occupy the orbits they do today. The loss of a large moon would subtly rearrange the system, altering gravitational relationships and leaving behind gaps where something once existed. Of course, the Chrysalis hypothesis is still a hypothesis. No fragment labeled Chrysalis has been found. No single piece of debris can be traced directly back to it. But the strength of the idea lies in how many questions it answers at once. Tilt, rings, moon orbits. Instead of treating them as separate problems, Chrysalis ties them together into a single, slow-moving story. One where Saturn's system evolved not through sudden catastrophe, but through gradual imbalance. A moon that existed for billions of years. A slow, orbital drift. A quiet crossing of a gravitational boundary. And then, absence. Saturn today carries no obvious scar from that loss. The planet still turns. The rings still shine. The remaining moons continue their steady paths. But the effects are there. In the angle of Saturn's spin. In the structure and brightness of the rings. In the architecture of the moon system itself. If Chrysalis once existed, then Saturn is not just shaped by what it has, but by what it lost. This idea changes how we think about stability in planetary systems. Worlds do not need dramatic impacts to change. They only need time. Gravitational relationships slowly shift. Resonances strengthen or fade. And eventually, something that once belonged no longer fits. Saturn's tilt may be the result of patience, not violence. A reminder that in the solar system, even giant planets evolve quietly, guided by forces that work too slowly to notice in a single lifetime. And if a moon named Chrysalis truly once circled Saturn, then its disappearance was not the end of a story. It was the reason the story looks the way it does today. A planet tilted, a ring system renewed, and a missing moon remembered only through motion. Which brings us to the final question. Not where Saturn's rings came from, but whether they are still disappearing. That question leads to what Cassini revealed next. For a long time, Saturn's rings were thought to be stable, slowly changing, but essentially safe in their orbit. Cassini challenged that idea. During its final years, the spacecraft detected something subtle but important. Material from the rings was falling into the planet. Not in chunks, not in streams you could see with a camera, but as a steady, invisible flow of particles guided by gravity and magnetic fields. This process became known as ring rain. Cassini measured charged water molecules and dust moving along Saturn's magnetic field lines, spiraling down into the upper atmosphere of Saturn. The particles originated in the rings and ended their journey far below, blending into the planet's clouds. The implication was unsettling. If the rings are losing material, then they are not permanent. Over long periods, ring rain could thin them out, slowly draining Saturn of one of its most iconic features. Estimates varied. Some suggested the rings could fade within a few 100 million years. Others proposed longer timescales. But the direction seemed clear. The rings were falling, yet the story did not settle there. As scientists looked closer, they noticed something odd. Despite constant bombardment by micrometeoroids, tiny grains of rock drifting through the solar system, Saturn's rings remain unusually bright and clean. If the rings were old and steadily collecting pollution, they should be much darker. They are not. This led to a second idea: pollution resistance. According to this view, the rings are not simply passive victims of incoming debris. They may actively recycle and refresh themselves. Collisions between ice particles can expose clean surfaces. Small grains may be ejected or migrate inward, leaving behind brighter ice. In this scenario, ring rain is not just loss. It is part of a balancing system. Material falls inward. Fresh ice is exposed. The rings remain bright. Some models suggest that electromagnetic forces play a role. Charged particles respond to Saturn's magnetic field, selectively removing darker contaminants while allowing larger icy chunks to remain. Others point to dynamics within the rings themselves. Dense regions may trap clean ice, while polluted particles are more easily scattered or absorbed by the planet. Both ideas attempt to explain the same observation. The rings look young, but the system behaves as if it has been around for a long time. So which is correct? Are Saturn's rings draining away, doomed to fade? Or are they self-cleaning, maintaining their appearance through constant motion and loss? Cassini did not deliver a final answer. What it did provide was evidence that both processes are happening at once. Ring rain is real. Material is falling. At the same time, the rings are dynamic. They collide, fragment, and reorganize. Brightness alone is not a reliable clock. A system can look young while being very old, if it has a way to renew itself. This creates a tension. If ring rain dominates, Saturn's rings are temporary, a spectacular phase in the planet's long life. If pollution resistance is strong enough, the rings could persist far longer than expected, changing shape but not disappearing entirely. The truth likely lies between these extremes. The rings are neither immortal nor fragile. They are in transition. Cassini showed that Saturn's system is not frozen in time. Moons shift, oceans breathe. Rings lose material and possibly regenerate. This matters because it reframes Saturn itself. The planet is not just wearing rings, it is interacting with them. Material flows inward, energy moves outward. Magnetic fields link space and atmosphere. Saturn and its rings form a single, connected system. Whether the rings are dying or renewing, one thing is clear: they are changing right now. And that realization brings us back to the theme that has followed Saturn throughout this journey. What looks stable from a distance often is not. Saturn's rings appear eternal. But Cassini revealed motion, loss, and renewal hidden in plain sight. The rings may be fading, or they may be cleaning themselves. Either way, they are not what we once thought. And that uncertainty, quiet, unresolved, and unfolding over time, is exactly what makes Saturn such a compelling world to watch. Because the most honest answer Cassini left us with is not certainty, it is awareness. Saturn is still changing, and we are only beginning to notice. For most of human history, Saturn appeared unchanged. Generation after generation looked up and saw the same pale light moving slowly against the stars. Even when telescopes revealed the rings, Saturn still felt permanent, fixed, reliable, immune to time. Cassini showed us something different. Saturn is not a finished picture. It is a process. The rings are not guaranteed to last. Material falls inward. Particles collide. Some ice is lost forever, while other regions remain bright, at least for now. The balance is delicate, shaped by gravity and motion that never truly stop. Moons change too. Some crack and cool, some breathe oceans into space, some carry scars from impacts billions of years old. Even Saturn's tilt, the angle that gives the planet its seasons, may be the result of slow gravitational change and the loss of a moon long gone. Not a sudden event, but a patient rearranging of motion over time. Nothing in this system is frozen. It only looks that way because change here happens slowly, far more slowly than a human lifetime. Saturn teaches us that stability can be an illusion created by scale. Cassini arrived at exactly the right moment to notice that illusion breaking. It watched storms form and fade. It tracked seasons shifting across the planet's clouds. It measured the mass of the rings, sampled their rain, and flew through the breadth of an ocean hidden beneath ice. Without Cassini, Saturn would still look eternal. With Cassini, we know better. We know the rings may thin. We know moons may evolve or fade. We know the system will not look the same forever. And yet, none of that makes Saturn fragile. It makes it alive, in the quiet, planetary sense of the word. Change does not mean danger. It means movement. Saturn changes on timescales that stretch beyond memory, beyond history, beyond concern. Its slow evolution will continue whether we watch or not. What Cassini gave us was not urgency. It gave us perspective. A reminder that we are seeing Saturn during a rare chapter, when its rings are still bright, when its moons are still active, when its system is rich with motion and contrast. A chapter that will eventually pass, but not tonight. Tonight, Saturn will continue its slow turn. The rings will keep circling. The moons will follow their paths, silent and steady. Nothing requires your attention. Nothing demands action. While Saturn slowly changes across millions of years, you exist in a much smaller moment, one that does not need to carry the weight of the cosmos. Cassini has already done the watching. The measurements have been taken. The questions have been asked. The story has been preserved. All that remains now is the quiet understanding that the universe does not rush, and neither do you have to. Saturn is not what we once thought, but tonight, it doesn't need to be. While the planet continues its patient evolution, you can let your thoughts slow, your breathing soften, and your mind drift gently away from motion and into rest. The universe is vast. Time is deep. And for this rare moment, everything you need to do is already done.